Hello my peers, welcome to this video. In this chapter, I'm going to talk about integration and integrals. But before we get into the concept of integration itself, we have to understand and know a very fundamental concept, which is the concept of areas and distances. Let's just recall some of the basic formulas where we can calculate some of the basic and easy geometric shapes, such as rectangles and triangles. We know the area of a rectangle is calculated just basically by multiplying the width by its length. And the triangle is basically half times the base times the height of that triangle. But the question is, what if we get some weird shapes where we don't really have a formula for that? Like this one here. It sounds and it looks that there isn't any formula for this one. That's right, we don't know a formula for this shape. But the thing that we can do just to simplify the process of finding the area of this geometric shape is just dividing the shape into many different areas where we can find their areas and just basically adding those sub areas together. Let's do that together and give it a try. So the first one is going to be this triangle, right? The other one going to be this triangle. Oh, that's good. The other one going to be these two triangles. Wow. So we divided a single shape into 4 different triangles. Let's just name them T1, T2, T3, and T4. And let's name the whole shape as, like, say, like D or any other thing. So now I can write the area of the shape D is equal to the area of T1 plus the area of T2 plus the area of T3 plus the area of T4. How to find the area of T1, T2, T3, and T4? They are triangles. We just defined the area, we define and know the area of triangle. It's half times base times height. So if we have the base and height, we can easily calculate the area of the whole shape by adding all of those sub areas together. We perhaps can use the previous method to find the area of this well-known shape, which is a rectangle. We actually know how to find and calculate the area of a rectangle, which is length times width. But let's look at this by using the previous method. So I can actually say that this rectangle consists of 8 small squares. And if I add the areas of those small squares together, I'm going to get the area of the whole shape, which is the rectangle. So let's do that together though. So I can say the area of the rectangle is actually S1, S2, S3, S4, S5, 6, 7, 8. So I'm going to say the area of the rectangle is the sum of the areas of S1, S2, S3 up to S8. So yeah, let's find the area of these. We know the area of the square is basically side squared. What is a side? The side is 1 unit. So 1 square is 1. And we know that all of the squares are the same, have the same area. So I can actually multiply 8 times 1, which will give me 8. But is this the same as calculating and saying that the area of a rectangle from the beginning is length times width? Yeah, it is. The length is 4 units, right here is 4, and the width is 2 units. So if from the beginning I say 4 times 2 gives me 8, which is the same as this one. So this method works. I can divide like a whole area where I can't find a formula for that to calculate the area. I can just divide that into many shapes where I can calculate those shapes areas, and just basically by adding those together, I'm going to get the area of the whole shape where I can't find a formula for. But sorry guys to say that, but this method doesn't work all the time. Like for calculating the area under this graph, I cannot really divide this into many noun geometric shapes to calculate their areas and add them together to get the area of the whole shape. Can I? I can't. This is the usage of integration. We use integration to calculate the area under the graph. So yes, but for now, we can kind of estimate the area under this graph by using some of the available methods. Let's try to do some of them together. The first one is basically counting the squares, as we did for this rectangle. Let's try to count the squares under this graph. So let's count them together. Basically, the area under this graph going to be here. So here one, this one. So it's bounded by this line and the x-axis and the function itself, which is x squared. So it's a quadratic function, but the domain is from 0 to 2. Let's count the squares together. So basically this is the first square. I can say this is square right here. I can just put it with kinda this one right here. This will give me 2. So this is the first one. This is the second square. So yeah, and this is kind of like 2 and maybe half, right? So I can probably say like the area is somewhere around 2.5. But let's say that the area is greater than 2, because we are sure about the 2, but we are not sure about how greater, like how much greater than 2. But this is a question. How much greater than 2? Like how can I know the range of this estimation? Like is how much greater? Like greater by 1 million, 1,000, greater by 1, 2? Like how much greater than 2? This is the question where we have to answer that. So that's the reason I'm going to like draw a triangle right here, and I'm going to find the area of this triangle. So the area of this triangle going to be basically half times the base times the height. It's going to be half times the base, which is 2 units. So this is 1, this is 2, times 2. What is the height? Is 4 units right here. So this will give me 4. Wow. So now I can say that the area is less than 4 because the graph is located like just below the triangle. So I'm pretty sure that the area is less than 4. And on the other hand, we know the area is greater than 2. So I can conclude that the area of this graph is somewhere between 2 and 4. So we somehow kind of estimated the range of the area under this graph by using this method. But the thing is, we cannot really draw triangles and count the squares under all the functions. This process really takes a lot of time and effort, and that's not really accurate. I'm going to talk about another method. That method is not accurate as well, but that's kind of just an estimation, just to know and understand, like, okay, what is the area under that graph? That method is used by rectangles, 2 right rectangles. Oh, what does that number mean, and what does that direction mean, right or left? I'm going to explain that in a few seconds. Well, first of all, the number here is saying that, okay, divide the domain under the graph into that number, and let's have that number of rectangles and draw those under the graph. And the direction says that the top right here is right. So the top right of the rectangle should touch the curve. Let's do that together. So basically the domain is 2. I'm going to divide the domain into 2 because it says 2 right rectangles. So the domain is 2. I'm going to divide it into 2 rectangles. So the width of each rectangle going to be 1. So basically the width is calculated by, I'm going to say 2 minus 0. This is the domain of my function, so this is 0 and this is 2. 2 minus 0 divided by the number of rectangles. So it's going to be 1. This one is the width of my rectangle. So now I know that the width of rectangle is 1. So this one is the width of my rectangle. What does this right mean here? The right means is when you draw your rectangle, okay, its right corner should touch the curve. When it touches the curve, as you can see here, just continue to draw your rectangle. This is what it is. The other one has the same width of 1, and continue to draw your rectangle. When it touches the curve, continue and draw that. So yeah, this is what it is. But what is the area? This is just the sum of the area of those two rectangles. What are that? The width, which is 1, times what? What is the height of this rectangle? How can I know that? I don't really have it, but I have the graph. The graph is x squared, so the height is going to be f of x. Wow, what is my x? It is 1 right here. So I'm going to replace x with 1. Plus what? Plus the width of my rectangle, of this rectangle, the second one, times its height. What is the height of this one? It is f of 2. F of 2. If I calculate and add those together, I'm going to get the area under this graph. So 1 times f of 1, if I enter 1 into this equation, I'm going to get 1. So 1 times 1 plus 1 times f of 2. So 2, if gets plugged in this one here, I'm going to get 4. So 4 times 1, 4, plus 1, 5. So I got 5. But the thing is, the rectangles are located over my length, over the function. So now I know that the area of this one, which is 5, is kinda overestimated. Yeah, it is. We use right rectangles. In this method, we use 2 right rectangles to estimate the area under this one. So now, by drawing the right rectangles, we kind of understood that this method on this graph is kind of overestimated the area. So we kind of find that the area is 5, but we know that the area is less than 5. Kind of we say that this is overestimated because we cannot really calculate the area under this graph by using any other methods except the integration, which we're going to talk about later. So yeah, let's do another one. But now we're going to use both right and left rectangles, but now 4, not 2. And let's see the difference between right and left and 2 and 4. So I'm going to start with the right because we're familiar with that. So yeah, now I know my domain is from 0 to 2. So now I know that the width going to be my domain. So if your domain is just basically from A to B, you can just say b minus a over the number of rectangles. So this would give you what? B minus a, b is 2, minus a, which is 0, over the number of rectangles, which is 4, will give me 1/2. So now I know that the width of my rectangles is 1/2. So what should I do right here? The thing that I'm going to do is basically divide the domain into half units. So this is half, this is 1/2, this is 1, this is 3 over 2, and this is 2, right? So let's draw the rectangle together though. So I'm going to here, continuing up. When it touches the curve, I'm going to draw my rectangle. I'm going to do the same thing right here. It touches the curve, continue to draw my rectangle. It touches the curve right here. I'm going to continue drawing my rectangle. Then it continues here, and finally this will go up here, and this will be this one right here. So now I'm going to say the area under the graph going to be the sum of the area of those 4 rectangles. So the width times the height of each one. So the width is half, I'm talking about the first rectangle, times f of 1/2, which is the height of this one, plus the second rectangle, its width, which is 1/2, times what? Times its height, which is f of 1 right here, plus what? Plus 1/2 times f of 3 over 2, which is the height of this rectangle, times its width, plus 1/2 times f of 2, which is the last rectangle. Let's do them together though. So 1/2 times f of 1/2. So 1/2 if get plugged here, I'm gonna get 1 over 4 plus half times 1 plus half times 3 over 2 times squared. I'm gonna get 9 over 4 plus this one right here is going to be 1/2 times 2 squared, going to be 4. So let's do that together. This would be 1 over 8 plus 1 over 2 plus 9 over 8 plus 2. So I'm going to take a common denominator, which is 8. This one will stay the same 1. This will be 4. This will stay 9. And this will be 16. So it's going to be 16 and 4, 20, 21 plus 9. It's going to get 30 over 8. But I know that this one is overestimated. Let's do the left one right here. I shouldn't do the calculation right here. It's fine, I can move it. Sorry about the mess. Just a second. Yeah, I'm going to just take the rest right here. I'm going to change the color and do the other ones. Okay, of this one right here. So I'm now going to apply the left rectangles right here. The thing is, now do the opposite thing. Draw, understand your domain. What is your domain? Divide the domain into the rectangle's width. Now I know that the rectangle's width are 1/2, so I'm going to divide the domain into 1/2 units. 1/2, 1, 3 over 2, and 2. Now we're gonna do the opposite thing. So the left top corner of that rectangle should touch the curve. So the left one. So I'm going to start from the right or from the left. It doesn't matter. So this one here. So the left one, it goes up. It touches the curve. I'm going to now draw the rectangle. Sorry about this one. Yeah. It goes here. The left corner touches the curve. I'm going to continue drawing it. It goes here. And this is basically what it is. And the left one is already 0 because the left corner just at 0. So let's try to estimate that by using this method. So the thing is, I'm not going to include this one in my calculations because this doesn't have any height, and yeah, it's already 0. So the area going to be 0 times f of 0, not 0 actually, sorry. It should be width, which is 1/2. 1/2 times f of 0 plus 1/2 times f of 1/2 plus 1/2 times f of 1, 1/2 times f of 3 over 2. Do we have anything, any rectangle on f of 2? No, we don't. This is the difference between right and left. So we started here from 0, like from 1 over 2 up to 2, but now we started from 0 up to 3 over 2. Let's do the calculations together. So thing is going to be this one here, 0. This one will give me 1 over 4. This one will give me, sorry, this would be 1 over 8 right here, because this would be 1 over 2 times 1 over 4, which would be 1 over 8. 1 over 2 times 1 will be 1 over 2. This one will be 1 over 2 times 9 over 4. So this will give me what? This will give me 1 over 8. Wait a second, 1 over 8 plus 1 over 4, 1 over 2 plus 9 over 8. this one here will be 8, 1 plus 4 plus 9. This will give me 14 over 8, which I know this one is underestimation. The reason I'm saying underestimation is because the rectangles are located like below the graph, so now I'm 100% sure that the area is greater than this one. So I'm basically going to write that this is underestimation. And now I can conclude that my area is somewhere between 30 over 8 with maximum and 14 over 8 minimum. 14 over 8 is basically going to be somewhere less than 2. So yeah, and 13 over 8 basically going to be somewhere less than 4. So somewhere between 2 and 4. So this is the same as right here, right? So yeah, this is what it is. Thank you so much. Hope to see you next videos.